like applications, yes, there will be actual, like real world, like word problem type applications. I always have that at the end of each year. But this is the common title for these problems that we do and these concepts. The applications are really graphical applications. So if you want to make a note of that, or you'll see it very quickly here, we're doing applications of calculus graphically for functions. This unit is a non-graphic calculator. You can have your scientific calculator. Because a lot of what we're going to do is doing stuff that the calculator can do, but we're going to do it with calculus. So that's a nice application. Well, let's jump in today. Extreme values. Extreme values are the ones that like n, the most extreme. And when we're looking at functions on a graph, the extreme values are the what we call extrema, meaning maximum and minimum values. So that's pretty much all we're looking at today, maximum and minimum of a function. If you remember from Algebra 2, there was a way that you did it just for parabolas. That was it. There's a little formula. Okay. Like negative b over 2a, if it was quadratic, and that was negative b over 2a. But that was only quadratic. So we can do any function. Doesn't matter what it is. And we can find the max or min of it. Before we do that, there's some vocab we need to know. First thing is global, also known as absolute extrema, versus relative, also known as local extrema. Global or absolute, let's refer to this diagram kind of in the middle of the page. So for this function right here, it stops at these endpoints there. The global max would occur at this, I'll just call it C. The global max or absolute max occurs at C, and its maximum value is here. So the max is the y value. It occurs at the x value. So you can see how here it's the overall max for the function. None are going to be bigger than it. Same here. This is the global or absolute minimum. There is no other smaller value for the function. And that's what we define global or absolute max and then to be. Here's the mathematical way we write it. F of C, that's the y value. So we're at C, and it's going to be a global or absolute max if the y coordinate, F of C, is bigger, greater than or equal to any other y values, f of x, in the function. So all of the other functions are less than this value in the domain. So for all the domain. Now, it's absolute, that's supposed to say minimum, I'm sorry. It's absolute minimum, it's fine on here as I'm looking at it. Absolute minimum if your value, your y value, is less than all the other values. So all the other values are bigger than it in the domain. Contrast that with relative max and min. Relative is like you have a hill or a valley. Like here's a hill, yeah. So that on this, like right around here, it's certainly a little maximum. But it's not the biggest value. There's many other bigger values over here. So it's what we define it as is it's local or relative max. If it's a maximum on some interval. That's really what we say. So like on this interval from here to here, yeah, it's a maximum. It's maximum just on that interval, but not on the entire domain. So there's a little change up here in this definition. Instead of in the entire domain, it comes down here. We say on some open interval. So it's the same as before, same definition, but it's on some local interval. That's kind of the vocab to start. Anything else I can clarify there, or any questions on just the terms? Okay, so we'll find some maximums soon. The next thing, though, is the extreme value theorem. Now, what we're going to have, let me jump to the next page for a minute. You don't have to flip there. Sometimes we'll have functions, it just says here, find the max or min. So the domain is all real numbers. I should say all real numbers in the domain. And this domain is all real numbers. So it's all real numbers in the domain. Other times it will say find the max and min, the extrema, on an interval, on a closed interval, -2, 3. So what this theorem says, let me go back, the extreme value theorem. if you have a continuous function and you're on a closed interval, like that second one, AB, it is guaranteed you have both a max and a min. It's guaranteed to have a max and a min. There's a simple example right here. This function is continuous. It's on this closed interval. I'll say this is A and this is B. It's got to have a max and a min. Here's the minimum, and here's the maximum. We can actually call it a global max and global min because it's global on our restricted domain. So continuous and on a closed interval. You might say, all right, well, what if it's not continuous or what if it's not closed? And I'll show you why those don't work. The first, let me first do if it wasn't on a closed interval. So this one right here is on the interval 0 to 1, on an open interval. So it doesn't include 0 to 1. So I say, yeah, watch out, not all functions have a max or a min. So right here, if you said, if I try to say, all right, the maximum values of this function is the y coordinate, it's right here, right? And I'd say, well, this is 1. So I'd say the maximum is 0.9. But then you might say, well, isn't it 0.99? And then I would say, well, it's actually closer, it's 0.99. You see what I'm saying? Like, it never actually, you could always name a bigger value as long as you don't go past 1. So if you're on an open interval, you can never get an exact value. You keep on going, and it doesn't ever settle down on an exact value. So that doesn't work. So it has to be closed interval. You might say, what about this one? Why does that be continuous? Simple answer is an asymptote. So let's say I had a function like this, and there was an asymptote here. Okay, it went kind of like that. This one is not continuous. It doesn't have a max or a min. It doesn't have a max because it's going up along the asymptote. It's going up to along infinity. So the limit at, maybe this is 4. The limit at 4 does not exist. The limit from the left is infinity. But there's no maximum value. It just keeps going up forever. And saying there's no minimum value, it goes down forever. So that's why it has to be a closed interval and a continuous function. If so, then it will be then you are guaranteed a max and min. Okay, any thoughts before now I tell you how we find them? The extreme value thing, that'll be useful. We'll see it in an example too. All right, finally, extreme values occur. So how do we find them? 3 possible locations. The first is at endpoints. So right here is a prime example of that. On this graph here, the minimum was at the endpoint. It was at A. So, we call these critical points. I'm sorry, I don't think I said that. Critical points are basically where extreme values occur. Okay? That's right here. Extreme values occur at critical points. There's 3 of them. So the first is endpoints. The second 2 are both based on the derivative. So you first see if there's endpoints, then check the derivative, and they're both based on that. The first one we call stationary points. We have been doing this since Unit 3. It's those problems where I say, find where the tangent is horizontal. Because here's a function right here, when the slope, isn't the slope 0 right there? Isn't that where there's a local max? A maximum right there. That's where the slope is 0. So we've actually we've done these before. Not a ton, but we've done them. Same here, there's a local minimum. Right there, I could keep going with some others. Alright, but, or maybe it was global max. Basically, do the derivative and you set it equal to 0. That's a stationary point. You could say something about that's a horizontal tangent. Okay, another one is singular points, when the derivative does not exist. Now, these are not guaranteed. These are possible locations for max and min. Let me show you very quickly why. if I had an x cubed like function, just straight x cubed, right here, the slope is temporarily 0. But that's not a max or a min. So we'll talk more about this coming up soon, but what we're finding right now is possible locations for max and min, and most of them will work for our purposes. So let me finish up right here. So singular points. Perfect example of that one is absolute value of x. We talked about there's a corner right here, right at 0. Corner. Derivatives don't exist at corners. And so right there, isn't that the minimum? The minimum of that function. So this is an example of where you do the derivative, where does it not exist? At 0. Well, that's the minimum. So those are the 3 endpoints when the slope is 0, stationary points, and then singular points when the derivative does not exist. All right, we're going to find some now. So now we're just going to do several examples. Is there any answer on that one? Thoughts, critical points? Okay, let's flip it over and let's try some. Alright, so basically I'm asking you on these, find the extreme values. Pretty much every question here. Find the extreme values. Sometimes they say that, sometimes that's an action then. Moving forward, guys, we will have a test to know if it's global or local. Okay? If it's the overall absolute max and min, or if it's a local one. For now, there's some ways we'll know. Now I'll talk about it. But for now, we're just going to find a max and min general, the global ones if we can. Okay, so find the max and min for this function. It's just on its domain. It's on its domain. It doesn't say on a closed interval like a number 2. So there are no endpoints. So I'm just going to write this out for our first few times we do this. I won't always write it out in the future, but I'm checking endpoints. And there are none, because there's no closed interval. Just the whole domain. So then I check stationary and singular points. And for both of these, I need f prime. So let's do f prime. Power rule, negative 6x squared plus 6x. Now we look at it, and let me go ahead and knock out singular points. This is the derivative. We need where it doesn't exist. There is none. This is a polynomial. Right? This would be a parabola if I graphed it. It's just everywhere in this domain. It's the domain is all the numbers for this function. So there will be no singular points on this one because the derivative is good. We'll see it in number 2 where we'll have some singular points. So we see to check the stationary points. That's where f prime equals 0. And so this is a horizontal tangent question. I'm just finding where the derivative is equal to 0. So I'm setting it equal to 0. Now I'm going to just go ahead and start to solve this. On the right side, I solve. And I will factor. I'm going to factor out a negative 6x. So here I'll be left with x, 6x divided by 6x, negative 1. And we solve each of these. I said x minus 1 equal to 0, and I'll get 1. And I said negative 6x equal to 0, divided by negative 6, so I'll get 0. Okay, very important, we'll see this on a later one here, but if it was just negative 6, you would get negative 6 equal to 0, and that would not give you anything. It would not give you 0. So sometimes students, it's like, they factor it, they get down to something like this, and they want to say, oh, well, this one gives us x equals 0. No, it would give you 3 equals 0, which doesn't give you any solutions. Okay, so for our purposes, we have 0 and 1. Those are the x coordinates for the critical points. Now, we need the overall max and min values, and so we need the y coordinates. So what I like to just make a little table. Basically, you just need to plug them in now. You don't have to make a table. It's just my way of organizing it. I'm just going to choose our critical points of 0 and 1. And I've plugged them in to get the f of x, the y values. I plug them into, I want the y value of the function. That's the max. So I plug it into the original function. So I'm plugging I'll start with 0. I'm plugging 0 in. I'm doing f of 0. Well, I'll get 0, right? 0 cubed times 0 times -2, 0. 0 for the second one. Then I plug in 1. 1 cubed is 1 times -2 is -2. 1 squared is 1 times 3 is 3. So we get 1. So let's write down our final answer now, the maximum and minimum values. I will put that there is the largest y value is the maximum. Okay, there's a couple ways you can write this. You can write it as the full point, or you could say the maximum is this, 1, and it occurs at x equals 1. So I think I'm just going to put the point for this one. Maybe on the next one I'll switch it up. The min is the lowest value, 0, 0. So again, what this means is the max is at 1, it occurs at x equals 1. The min is 0, it occurs at x equals 0. Now for this, some of these we can clarify global versus local. And on this one we can. Because it's a negative x cubed function. Looks like this. These don't have, these go on forever. Right, up and down. There is no max or min, like global, sorry. There's no global maximum, they go on forever. Therefore, these are local. Okay, what we just found is like this point here and this point there. Local, or you can say relative. Okay, not all, some of these you're just going to say maximum, some of them we will know if it's a local or global. That's our first one. Let's see, any thoughts? Anything I can add, clarify that one? Okay. Let's keep going. Let's do a couple more then, just so we see the process. And there'll be some differences you'll see as we go along. So first thing about number 2, same question, different function. Here's the new thing. It's on a closed interval. So what that means for our critical points is we will have endpoints. So that's on an x interval, from x being -2 to x being 3. So I'm just going to put, x equals -2 to x equals 3. Those are critical points. So let me do this, just so we don't, sometimes students forget those. They do not remember. So I'm just going to draw them in first, like -2 and 3 are going to be 2 of our critical points. So I can plug them in now. I'm just going to wait once I get some more. So let's go to here. I need to find f prime to look at the stationary and singular points. All right, so do f prime. We do a power rule. X to the 2/3. No chain rule here. Just bring the 2/3 down. X. And I subtract 1, so it's to the -1/3 power. Now, well, I guess you can set it equal to 0 already if you want. I'm just going to write it as f prime. Let's move this, right? We want to change it to a positive exponent. Here's an important time when we need to. So the numerator is 2, the denominator is 3, but now it has a positive x to the 1/3. Okay, now here's a good rule of thumb for this. If you have a fraction, stationary is the numerator, singular is the denominator. So what I mean by this is, like, we're going to set it equal to 0, right, like we did in the last one. To get the stationary points, you're really just setting the numerator equal to 0. So for this one, stationary, I do 0 equal to 2. And of course, that doesn't give me any solutions. So basically, there are no stationary points. There's no stationary points. Singular, though, there will be. So this one I set the denominator equals 0. 3x to the 1/3 equals 0. This one will work. So we divide by 3, both sides. So we get x to the 1/3 equals 0. So divide by 3 is 0. And this is really cube root, x to the 1/3. So just finish this one up. I will cube both sides. Raise both sides to the 3rd power. And it's really a cube root. Or you can think of it, this will become 3 over 3. 1/3 times 3 would be 1, 3, 3. So it'll be x, and then over here it'll be 0. So basically I add this to my list of critical points. 0 is a singular point. It's kind of like the absolute value. We found, this found where the derivative does not exist. That's what we just did. Oh, and here, I want to go back up here. Doesn't that kind of make sense? What I did was I found kind of like a domain question back from Algebra 2. Like when you have a fraction and you said, where's the domain? Well, you find where the denominator is equal to 0. That's where the domain would not be a domain of that value. Okay, so really just to sum up, if you get a fraction, the numerator set equal to 0, that's 1. Denominator set equal to 0, that's another. And that would each be stationary and singular. Okay, to finish up, it is now the same as the first one. These are your 3 critical points, and you plug them in and find your max and min. Let's start with 0. 0 to the 2/3 power is 0. Next one, let's do 3. 3 to the 2/3 power is 3 to the 2/3. Now, it might be a good idea to get an idea of what that number is, close approximation. So let me tell you, I don't want to spend too much time plugging things in today. So you plug in 3, you get about 2.080. And when you plug in -2 to the 2/3, it's 1.587. Making sure to do -2 in parentheses to the 2/3. All right, so now we can write down the max and min. I'll start with the max. It's the biggest y value. Now again, you can write down the full point. So the full point is this: 3, 2.80, 2.080. Just the maximum is the y coordinate. So you can say the max is 2.080 at x equals 3. Oh, I said I was going to do that in this one. If you already wrote this down, that's fine. I said I was going to do it this way. The max is 2.080 at x equals 3. And the min, the smallest one, 0. 0 at x equals 0. Oh, one other thing on this. So once you get that, think about can you know if it's a max or a min? I'm sorry. Can you know if it's a global max or a global min, or relative? And this one's a closed interval, so we will say it's global because we are just on this given domain, a given interval, and so it's absolute or global max and mins. By the way, this endpoint one, it just was there. It's just nothing. Good, because this one was bigger than it, the 2.080. Okay. Bless you. I think I'd like to do the next. Let me do the next 2 to finish up on the next page. One is a little different than I did earlier. What I might do is over the weekend, we'll come back in, and then on Monday I might do one of these, or one number 3, or the one from the practice. Yeah. The one from the practice. Okay. Yeah, so your thoughts on the first 2. Okay, let me finish up with these next 2 on page 3. Notice this says find the extreme values. Okay, first of all, this one's piecewise. Right, so it's slightly different here. It's a function's a line, x plus 2. We can even graph the basic function if we want. Everything to the right of 1 is x plus 2. So here's 2, so it's a line. It's going up like this. And then everything less than or equal to 1 is 5 minus 2x squared. It's a parabola upside down because it's negative. So it's something to the effect of like this. We don't know exactly. It could stop here. It's a parabola, but it stops. So something to this effect. Oh gosh. And it is filled in because it's less than. I'm just giving you an idea of what this one looks like. Because it's piecewise. Well, first thing I'm going to do is get my critical points. Oh, and we're on the entire domain. So here, I should write this down. Critical points. There are no inputs. Okay, because we're on the entire domain. So then I need to look at stationary and singular. So this where f prime is 0, and this one's where f prime does not exist. So let's start with doing the derivative, and then we'll see where f prime equals 0. Alright, so we'll write our derivative piecewise, just like the function was. And so the derivative, 5 minus 2x squared, we got 0, and then negative 4x. And this is when x is less than 1. The next one, the derivative of x plus 2 is 1 and 0. This is when x is greater than 1. Alright, so from that, I need to set each of them equal to 0 and see if it gives me any critical points. So I can set each part of this equal to 0. So the first one, I set 0 equal to negative 4x. And this will yield us a good one. Divide by negative 4. 0 over negative 4, I get x equals 0. So I'm just going to make my table. Just start plugging. I have no endpoints, but I do have a critical point there. Alright, the other one, 1. I set that equal to 0. That doesn't give me anything. Okay, so no solution. No solution from that one. So from that, I got 0. So any thoughts on that? Like how that was a stationary point. Good on that so far? Then I need to look, so I kind of did these separately this time, but it's still based on the derivative. I need to see if there's any singular points. Oh. I need to see if the derivative does not exist. Now, guys, with stationary points, so this one, do you remember like derivative doesn't exist when there's a corner or a cusp, so like curve, vertical tangent, or the most common one, discontinuity. So there's no derivative that exists if the function is not continuous at that value. So what I need to see is it even continuous at 1. This is 1. So let's go back. This is now, it's kind of a limit problem. It's continuity. Just to check if it's continuous, I just plug in the 1s. I just see if it's continuous at 1, what the y values are. So I'm going back to the original function. I'll plug in 1 here. It's 3. Plug in 1 there. 1 squared is 1 times 2, so it's 5 minus 2. It's 3. So actually my drawing, let's see if I can move it down here. Okay. It actually is connected. Right, so it's continuous. This one's actually good here. It actually is continuous, so that's good. Now, you have to check one more thing. Is it a corner or a cusp? Because the slopes could be different. Right? And it kind of looks like it is. Based on that, it doesn't look like the slopes are the same. Which actually, definitely, it's going to be. So let me go back up here. Oh, no, sorry, not that one. This one. I need to check if the slopes, the derivative, see if the slopes are the same. So I plug in 1 again, finding the slope at 1. Here it's just 1. Can't change that. Here the slope is 1 times -4, -4. So basically, as we can see here, you have the slope on this side is 1, the slope here is -4 from the left. They're different, therefore at x equals 1, there is a critical point. So we have to check each of those. Those are the only possible max and mins. All that's left is to do is plug in 0 and 1 into the original. So 0, I got to go to the correct function. It's this one, less than 1. So I'm plugging 0 in here. That'll be 0 squared, 0. Plus 2 is 0. 5 minus 0 is 5. Okay, now I plug in 1. Again, I'm going to get the top function because that's less than or equal to 1. 1 squared is 1. Times 2 is 2, so 5 minus 2 is 3. And so what we see here is this is the max at 0, the max is 5 at 1, and the min is 3. So let's write it down. How about I'll go back, I'll just write the point this time. The max is 0, 5, the min is 1. And let's see what else I want to say about that. Oh, because I was able to kind of map out the function here, what it looked like, it looks like this. We saw that this one at 1, that was a min. Here's a local min here. And at 0, it was 5, and that ended up being a local max. So what I can say here is I'm going to add a local, or a relative. Again, moving forward, there will be more ways to determine if it's global or local. For now, I'm just using some kind of like context, what the graph looked like. Okay. That was a very different one than what we've seen. Definitely the critical point. No endpoints. Did the derivative, found one critical point, 0. Then I had to look at where the derivative does not exist. And it didn't exist at 1 because the slopes were different. One more? Anything to answer on that one? Okay. Last one was for today. Let's find the extreme values of x squared minus 8 natural log x on 1/4. On 1/4. So, first thing, I'm looking at critical points, and I do have some endpoints. X equals 1, x equals 1. So I like to just map these. I'm going to plug in 1, I'll plug in 4 soon. Okay, now I'm going to look for my stationary and singular points, and so I need to do f prime. Let's do f prime of x. So derivative, 2x minus, bring down the 8, and then the derivative of ln x is 1 over x. Yeah, I'm going to write it as 8 over x in a second. Yeah, so I'm going to set it equal to 0. And go from there. So I'm going to make it 8 over x. That's all right. I got to do that originally. 8 over x. So prime there, f prime. Okay, so I'm going to solve this. I did the derivative, set it equal to 0. I'm solving. You can clear the denominator now. I'm going to just go ahead and add this term, 8 over x, to both sides. Or I can subtract 2x. I'm just getting 1 to one side and the other to the other side. So I've got 8 over x equals 2x. Now I need to clear the denominator or cross multiply. It's going to be the same thing here. I'll just clear it by multiplying by x. So I got 8 equals 2x squared. And you can probably see this one's going to work out because we're going to divide by 2. Get 4 equals x squared. And I do a square root for both sides. And don't forget when you're doing square root to both sides, it's plus or minus. So I get plus or minus 2. Okay. Now, let me go back up. Plus and minus 2. Certainly 2 is good, between 1 and 4. I'm not going to put in negative 2, though, because it's not in our interval. Okay, so if you want to make a note, like why I'm not doing negative 2, it's not in the interval. So I'm not putting that in as one. Okay. Now, one other thing before I plug these values in, so I did endpoints. That was 1 and 4. I really just got where the derivative is 0. So I just got stationary points. That was 2. I do need to think about this one. Where did the derivative not exist? Okay, so let's go back to my first. Here was the derivative. Here's the derivative. Is there a value of the derivative where it wouldn't exist? An x value that wouldn't make that work?
I don't know.
What if I gave you this function, and I said, forget the 2x, and I said, here, 8 over x, and I said, find the domain of that function. What would you say? You don't remember domain?
No. It's the x
Yeah.
value. Well, wouldn't it just be? Oh, it'd just be that, right?
Well, no, that's my function. What's the domain of this function? All real numbers, but somebody gotta help me out with domain.
I don't know.
I'm shocked. Domain. You did this all of last year, got into and freak out. Domain? Huh? Somebody's gotta help me out. The domain of this function is all the x values that work. And all of them work in the world except for one. 0. 23 works, so it could be 8 over 23. So, that's domain, right? Remember that now?
No.
Because if you put in 0, it'd be 8 over 0.
Yeah. I don't remember it, but I
You can't divide by 0.
Yeah, you can't divide by 0. So that's why I'm just showing you that example. So I go back here. What value would not make this one work? 0. So that's why over here you actually get a singular point. Actually, it's basically this. Singular points are basically just looking at the domain of your derivative. Now, do you want to make a note as well? I'm not going to write 0 over here because not in the interval. So yes, the critical points are at x equals 1, 4, 2, negative 2, and 0. Okay, but if you want to I don't have to do these two because they're not getting interval. Okay. Sounds good. Well, last thing is just plug them in. Let's plug in 1. So I'm going back to the original function. 1 squared is 1. You guys remember what ln of 1 is? It's 0. So it's 8 times 0, which is 0, so it's 1 minus 0, which is 1. And again, you would just plug the rest of them in. So you plug in 2, it'd be 4 minus 8 ln 2. Now to get a good idea of what that is, that you put in your calculator. And
It's like -1.5.
yeah, about -1.55. And then you put in 4. 4 squared is 16 minus 8 ln 4. largest value, and that's our max on this interval, and the smallest, since we are max, and the smallest one is this one on the interval. Okay. So, just write it over here. Let me write that other form. So I'm going to say maximum max at nope, maximum is 4.9 at x equals 1. Minimum. I'm going to abbreviate these. Negative 1.55 at x equals 2. One last thing I'll say is these are actually global, or let me write the other word, absolute global max. Because we're on a closed interval. All right. Any answer on that one?